recording. On your test, I'm sorry. There will be 12 functions given to you. Okay, 12. We call them parent functions because we're going to talk about transformations. We're talking about taking these 12 functions and sliding them, moving them, stretching them, shrinking them. Some of you hit on some of that in Algebra 2, and some of you haven't. And if you haven't, that's okay because I'm going to do it from the bottom up. But what you're going to have to do is you're going to have to know these 12 functions inside and out so that you can move them, shrink them, stretch them, and everything else. So you'll have to, for each function, okay, so you might want to write this down because I'm not going to give you this. This is exactly what your test will be on all of these, okay? I will give you the function. This is called functions you must know. They're just and so for each of these, I'll give you the equation, and I'll just start out with the very first one because it's the easiest. Y equals x. This is a linear function. Okay, why is it a linear function? What is it, graph? A line. It's a line. All right. So for each one of these on your test, I will give you that, and then you'll have to fill in not as much as what was on the last test for the analysis, but some of the same kind of high points. So we'll talk about it. First thing you have to do is graph it. And as part of your graph, you will have to do an X, Y, T chart of points used to graph this function. Now with a line, it's pretty easy because you only need how many points? Let's graph a line. 2. Does it matter what 2? No. Now if I get into quadratics and things like that, it matters what points I pick because I'll need like the vertex or other things there to graph. But for a line, I just need 2 points. So pick 2 random x values you want to use. What would you like? 1 and 2. If x is 1, what is y? 1. If x is 2, what is y? 2. This is the parent graph. Like that, all right? That's the graph. You're just using the points to. Oh, I don't know, but that's a point on there too. I don't know why I did that because I'm just, there you go. 1, 1, 2, 2. I don't know why I did 0, 0. There we go. All right. Tell me, and each one of these things are what you're going to have to answer for each parent graph, all right? What is the end behavior of this graph? Y'all can do this. There's how many ends of the graph? 2. A right end and a left end, right? All right. As x approaches positive infinity, which side is that describing? The right side. So on the right side, what is the graph doing? It goes up. That's positive. You can use y or f of x. I'm just using y because that's how it was defined here. Now, how about the left side? Negative infinity. All right, so far for each parent graph. T-chart, graph, in behavior. Is this continuous? Why? It's one straight line. I never have to pick my pencil up. I never have to move it. It just, shoop, it's a line, right? So yes, it is continuous, and because I don't have to lift my pencil up when I draw it. All right, so that's another thing. The last thing you'll have to do, nope, not the last thing, I lied. Another thing you have to do is the symmetry. And some of you got confused on symmetry. What are my possibilities for symmetry? Odd, even, or neither. How do you tell? Make the x negative and look at what it simplifies to. So if I make the x negative, how does that compare to this one? Same, completely opposite, or neither? Opposite. Opposite means odd. This has odd symmetry. Does that make sense to everybody? Yes, Alex is the only one shaking his head yes. Yep. Everybody else is okay. Final thing is domain and range. We just tend to draw an infinity sign and move on for domain and range for some reason. So clearly we need to talk about that a little bit more. Domain, everything that X can be left to right. So look at the line from left to right. What's the smallest X can be? The furthest left it ever goes. Negative infinity. Now take it up to the highest that X ever goes. Positive infinity. The range. To positive. Now, the difference in this test and the last test you took is I'm telling you it is going to be the 12 functions that I give you. I'm not going to give you the test before you go, but I will show you. This is what it looks like. The equation, the graph, and then the steps we just went through, the things we just went through. Okay? For all 12 parent functions. All right, so we're going to run through all 12. We'll do 6 today and 6 tomorrow. All right, let's do the next one. Y'all try to contain your excitement. This is number 1, yes. And they are the 12 that you have to be so familiar with that we will, for all future tests, it'll be assumed that you know. Now, you can even use your calculator on this. I don't care. So if you need to put in y equals x and look at the t-chart, fine. But you need to be very, very, very familiar with these. That's why we take the time out to test on them. All right, the second one is the absolute value. Notice on these, there's no numbers here, nothing added, subtracted, multiplied, divided. That's why they're parent graphs. All right, so let's graph it. Can you think, do you know, before we actually do this together, what the absolute value graph looks like when you graph it? Does anybody know? It's a V. Looks like a V. Okay. It's that same line. Absolute value means it's got to stay positive, right? So what it does is it takes this piece and it flips it up and makes it positive. Okay, and that's why it's a point there for the absolute value. So for this, you really need to pick, come on, that vertex sits at 0, 0. So for your t-chart, you'll need at least a point on either side of that. I'm going to go 2 points. So I'm going to go -2, -1, 0, 1, and 2. What do you get for y when x is -2? 2, positive 2. Only thing absolute value is doing is forcing positive. That's it. How about when it's -1? 0, 1, 1, 2, 2. Does that make sense to everybody? Plot those points. While y'all are doing your graph, was that other function bounded or unbounded? The line. Unbounded. Unbounded. Yeah, sorry. All right, how about the end behavior? Yeah. No. So, like, where do I get the x's or where do I get the y's? Okay, so the x's, I'm telling you which x's to pick, and you'll need to pick at least those same ones because I know where the vertexes. This is really just getting us familiar with the parent graphs. So I'm telling you which points are important for you to use in order to graph them. The y's are coming from plugging in here. All right, how about in behavior? All right, I'll write both of them. And then you tell me that. All right. So the write-in, as x goes to positive infinity, y goes to positive infinity. In behavior. And as x goes negative infinity, what does y do? Positive infinity. Why are they both positive? Both ends, that's exactly right. Both ends are going up. Does that make sense? Everybody's okay? Continuous or nah? Why? I don't have to pick my pencil up at all as I draw it. I can just connect it. Domain. You're right. That's right. Negative infinity. Remember, domain, I'm really looking for two things that are going to impact domain. A fraction and a radical. If you don't have either one of those, chances are it's negative infinity to infinity. How about the range? Bracket or parenthesis? Why? There's actually a point there. The range is 0 to infinity. From the bottom up, the lowest point on the graph up to the highest. So this lowest point is 0 and it goes up. Symmetry. All right. It turns into positive. So what happens? Look, whenever I plug in a negative x, absolute value is going to force it positive. It's even. It looks exactly the same as what I started with, so you're exactly right, it's even. Into some sticky ones tomorrow, not so much today. All right, number 3. You should be very familiar with this one. What's that look like when you graph it? Starts with a P. A parabola, right? This is the parent graph of the parabola. Before we move it, stretch it, shrink it, it's just our basic parabola, okay? Our vertex on the parent graph is always at 0, 0. So when I look at my table, I want to make sure that I include, I'm going to go 2 points left and 2 points right of the vertex. I'm going to use the same x points that I used for that absolute value, okay? So I'm going to go -2, -1, 0, 1, and 2. If I have -2, what is my corresponding y value? 4. How about -1? 0, 1, 2. Does that confuse anybody? All right. I should probably have moved this axis down some. There we go. 0, 0. 1, 1, -1, 1, 2, 3, and 4. Different than an absolute value because it kind of curves here instead of a sharp point. So there is my graph. Am I going too fast? Everybody good? All right, so I got my two ends. As x approaches positive infinity, what does the graph do? It goes to positive infinity. How about the other side? Both ends go up, right? Before we actually do it, if you just look at this graph, what kind of symmetry do you think it might have? Even. Remember, if you can fold it on the y-axis and it's the same on both sides, it's even. If you can cut it across this line, or straight in the middle, that shouldn't go like that. So, like that, and it's the same, then that's odd symmetry. Just a quick check as you look at visually at the graph, okay? But if I plug a negative in for x. When you square a negative, what happens? Turns it back positive, so I have x squared. And so it looks exactly the same, which tells me what? Yes, it was even. How about domain? These are easy. These first 6 are easy today, or should be for you. How about the range? 0 to infinity. Is it bounded? Yes. Above or below? Does it have below? That's right. Does it have a max or a min? Is it absolute or relative? Absolute. Is everybody good on that? Okay, so minimum because it bottoms out, right? It's got a low point. And it's an absolute minimum because there's absolutely no other point below that one. If there was another point below it, if it did something kind of like this, these are relative minimums. Okay. Not on the test, no, but on some of our work we're doing. Not on the must-know functions test anyway, maybe on the chapter 1 test, but not the must-know functions test. Is it continuous? Why? Don't have to pick up your pencils. Everybody good? Are y'all all with me? We're halfway through. Today. There's 12 altogether. We're going to do 6 today and 6 tomorrow. All right, next one. There's 2 functions on each side. So 2, 4. But I'm going ahead and print all 12 of them. Yeah, that's for y'all. Y'all worried about all that paper I'm printing over there in it?
I mean,
killing trees. It just prints kind of slow. All right, number 4. Number 4 is the radical function. Now we're going to get into some restrictiveness because of the radical. You okay, Maureen? You sure? Start brewing coffee when you come in here. Bless you. You want me to make you some coffee too? All right. Thinking about a radical, what can you never have under a radical? A negative number, right? That's going to impact whenever I graph. And my t-chart, it's going to impact my domain. I only want positives. Can I have 0? Can you have the square root of 0? Some of you are saying no. Some of you are looking kind of confused. Can you do the square root of 0? You can actually do the square root of 0. I'm going to do 0, 1, and 4. Now, why did I skip 2 and 3? They're not perfect squares. I'm going to make my life as easy as possible. Okay? And I'm not going to put 2 and 3 on here and get some nasty decimals. Uh-oh. I'm getting it. Thank you, though. All right. What's the square root of 0? What's the square root of 1? What's the square root of 4? So here are my points. 0, 0. 1, 1. 2, 4. Now the way this looks, if you think back to Algebra 2, is it kind of, that's terrible. 4, 2. I don't know what is going on. There we go. All right, here are my points. Everybody good with that? I didn't take it past the 0 because I can't go into negatives because I'm a radical, right? I'm losing some of you. I'm starting to see the glazed look come over some faces. I promise I'm almost done. In behavior is going to be a little bit different. Why? There's no negative. There's no left side of that graph. X never goes to negative infinity, right? So instead, I know I can go as X goes to positive infinity. What does the graph do? Positive infinity. It's going up. It's not going up very fast, but it's not asking me how fast it's going up. It's asking me, is it going up or down, right? Up, down, or to a number. That's what I'm looking at. I don't have another in there to describe as far as going on forever and ever. So I'm just going to leave it at that. Everybody okay with that? Yeah. All right. What's the domain? Yes. Yes. Bracket or parenthesis? That point is included at 0, 0, so it's included in my domain. So from 0 to infinity. How about the range? Same thing. Range is from the bottom up. Domain is left to right. Everybody okay on that? Mm-hmm. Is it continuous? Yeah. Yes, it is. It certainly is. How about symmetry? I hear odd and I hear neither. Which one is it? Neither. Because if I plug in negative for the x, I end up with an imaginary solution, right? And I'm not graphing imaginaries, but at the end of the day, they're not completely opposite and they're not exactly the same, so they're neither. If I look at it graphically, it's not symmetric either, which tells me it's neither. Everybody okay? Speak now, forever hold your peace. 2 more to go. All right, number 5. Cubic function. This one is odd. You're exactly right. This one's going to be odd. This one is centered about 0, 0, so I'm going to do my -2, -1, 0, 1, and 2. What is -2 to the 3rd power? -8. What is -1 to the 3rd power? -1. How about 0 to the 3rd? 1 to the 3rd? And 2 to the 3rd? Notice how they're keeping their same signs because it's a 3rd power, it's an odd power. All right. Let's graph them. This is 1, 1. Come on. 2, 8. -1 and -2. -8. And so when you construct this graph, it's kind of like a stretched out S. Okay? What's the domain here? Negative infinity to positive. How about the range? Same thing. Bottoms up. Continuous? Yes. How about in behavior? Positive. How about the left side? Anybody still struggling with that? What am I missing? Symmetry. Odd. That's exactly right. Because there's a third. When you raise something to the third power, it keeps a sign. So it's negative x to the third. It's exactly opposite, which tells me it is odd. Una más. Now we start getting into the fun ones. Remember, these have nothing done to them. These are the basic functions. We'll be taking these basic ones and sliding them up, down, left, right, stretching them, shrinking them. It'll be so much fun.
What?
That's what the projects are back there on the back wall. They took parent functions and transformed them.
Wait, we gotta do all that?
Wait, we did.
Maybe. Yeah, y'all
We
did.
did it.
Y'all didn't get quite as in-depth as last semester's did because we had enough time to really get into transformations. I'm thinking about it.
No.
Wait, we did this now?
Wait, yeah, about what?
Can I reuse my old
Those
one?
projects.
Legitimate algebra.
Can I reuse my old one? I don't remember.
I did Mickey Mouse.
Yeah. I think we did it in the second semester, not first. Were you first semester or second semester?
First. I was first. You were first.
All right. Now, this is what we call the reciprocal function, and we call it the reciprocal function because it's flipped over x, right? It's 1 over x. Now, on your last test, we talked about asymptotes. Remember that? We talked about horizontal asymptotes, we talked about top heavy, bottom heavy are the same,
Oh, yeah.
right? Okay. Tell me this.
I left you.
Where do vertical asymptotes occur? Okay, no, those are horizontal asymptotes. It's top
What do
heavy,
you mean by
bottom
would
heavy.
there occur?
How do you find vertical
Oh, it has to
asymptotes?
equal zero.
What has to equal
So the
zero?
denominator.
The bottom of the fraction, where the denominator equals 0, those are your vertical asymptotes, right?
Yeah.
Okay, so looking at this, I have a fraction. Okay, so I'm going to have an asymptote there in the bottom. So my vertical asymptote, I set the bottom equal to 0, and this is an easy one to set equal to 0. There's nothing to solve here, right? So this tells me I have a vertical asymptote at 0. Okay? Now, is it top heavy, bottom heavy, or the same? It's bottom heavy, right? It's got a degree of 0 up top and 1 on the bottom, so it's bottom heavy. When it's bottom heavy, it does have a horizontal asymptote. It has it at y equals 0. So my axes on this one are asymptotes. Everybody with me? No? Where'd I lose you, Shala? Okay, so that's any horizontal asymptote, what you're looking to see if the degree of the top is bigger than, smaller than, or the same as the degree of the bottom. You know what the degree is? The biggest exponent, right? So you don't see an exponent up here, but I could really write this as x to the 0 power. And this is x to the first. Right? So we had 3 scenarios. If it was top heavy, there was no asymptote. If it was bottom heavy, then y equals 0 was the asymptote. And if those 2 degrees were the same, we had to take and make a fraction out of the leading coefficients. And so we have to really find what situation is occurring there so we know what kind of asymptote it has. All right, so there are my two asymptotes. I did all that first because I need to know what kind of points to pick for my T-chart. I want to always go at least at a minimum of 2 points on either side of vertical asymptotes. Okay, so I want to at least go -2 and -1. I don't need zeros. It's going to be undefined at 0. If you plug in 0 here, you get 1 over 0, and that's undefined. So I'm going to skip on over and do 1 and 2. If you plug -2 in that equation, what do you get for y? -1/2. So -2, -1/2. How about if you plug in -1? -1, right? So -1, -1. How about if you plug in 1? Mm-hmm. How about if you plug in 2? That's right. Now, what do you know about asymptotes? The graph can never do what? It bounds it. That's right. It can't go past it. It can't go through it. But it hugs it. So if you think about that, there's only one way really to draw this. These look like kind of wings. They hug this side of the asymptote and this side of the asymptote. Several of you were confused on your test whenever you had asymptotes on there because your calculator was graphing them. That's why we have to be very, very aware of where our asymptotes are occurring so we can see them. All right, everybody okay on that parent graph? Before we do any more analysis on it. I know y'all are, y'all look rough. Like, is this too much?
I just
Young. All right, which part? The asymptotes or
It's just like you.
That word
wow.
is weird.
So you don't have to
the what's weird?
And it's a man.
Yeah, we're gonna do all that. I hadn't got there yet. I was just graphing it right
So
now.
since it's a fraction, you have to do the vertical and horizontal.
Correct, correct. Anytime you see a fraction that you're graphing, you need to start looking at asymptotes. Vertical's the easiest because we just set the bottom to 0, and then the horizontals are coming from that top heavy, bottom heavy or same. All right, we're going to get a little bit deeper here. How about the domain? You got to use the U. You're exactly right. I got to use the U because I'm leaving something out. You have to leave out the asymptotes. That's exactly right. So watch, as I move left to right, what's the furthest left that it goes? Negative infinity, right? And then it keeps going, keeps going, keeps going, keeps going, and stops. Right? Stops where? At 0. But it picks back up on the other side of 0, right? And it goes to infinity. So to say that, Ayana's right, I'm going to have to use my U. I know negative infinity, and then it goes to 0. But it doesn't actually touch 0. So I put a parenthesis, and I use a U to say this is part of the domain, but it also includes what's coming next. The U joins them together. It stands for union. So think about whenever you get married, union together. Sticks them together and says then pick back up at 0 and continue on to infinity. So to leave out just one value, I put the back-to-back parentheses with the U in the middle. Y'all okay on that? Okay, then what's the range? Exact same thing. Is it continuous? No. What type of discontinuity does it have? Yes, that's right. You're exactly right. If it's not continuous due to asymptotes, it's infinite discontinuity. Because it goes on forever. Each piece is continuous on its own. And we're gonna change that definition a little bit when we get a little bit further in, but not just yet. Right now, we'll keep it with infinite discontinuity. How about in behavior? It's also different here. As x approaches positive infinity, what is the graph doing? This one's different. Y is approaching, or the graph is approaching what? 0. That's the asymptote. The bigger x gets, the closer the graph gets to 0. Does that make sense? Look at the left side. As we look left, what's the graph doing? 0. Some of y'all are whispering 0. That's right, 0. Is it symmetric? Or what type of symmetry does it have? Why? Change the x is exactly opposite. Remember when we're talking about a fraction, we want either the top to be completely opposite or the bottom, not both. And the bottom's opposite. So we're good. That tells me opposite is odd. I can also look and see that it's reflective there, or symmetric there. Yes, no, maybe so.